I consider these 2 point charges. Point charge A over here on the right and point charge B. They're totally separated in space, so this is not one picture of 2 charges kind of together. It's just imagining 2 scenarios separately, but we're kind of visualizing them at the same time. So we see charge A sets up a potential around it in space. I've only drawn 3 isolines here, and I've labeled the potential on each line. Over here, charge B also sets up a potential around its space, and I've labeled the isolines here as well. Cool. First question. Are charges A and B positive charges or negative charges? Go ahead and answer. So pause the video and see if you get that. All right, hopefully you got it. And the answer is that they are both negative charges. And you should be able to see that because you would know that the potential set up by a point charge is equal to Q, K over R, where R is the distance from the point charge, K is the Coulomb's constant, and Q is the charge. And we need to plug in the plus or minus sign related to the charge to get the answer correct here. So we can see as we get further and further out, the potential is tending towards 0, which makes sense. As R gets larger, the potential at that point would go to 0. But because these numbers are all negative here, we've plugged in a negative amount of charge, giving us negative potentials. So we would have a negative amount of charge at this point, and we'd also have a certain amount of negative charge at that point as well. Okay, so question 1 done. Question 2 is a little more tricky. See if you can get this one as a good test of understanding. I want you to try to compare the magnitudes of the charge. So do you think one of the charges, is there more charge at points A and B respectively, or are they the same magnitude of charge? And be specific. If you think one of them has more charge, by what factor does it have more charge? Maybe you think charge A has 3 times as much charge as charge B, so you would say that. Or maybe you think B is 4 times as much charge as A, so you would say that. All right, pause the video and compare the magnitude of charge respectively between B and A. Go ahead. All right, now this one's a little more challenging. You have to pick out 2 points and kind of compare. So if we pick out these points I've labeled here, you can see that they both lie on their respective negative 90 volt isolines for both of them, right? So that means the potentials are the same at those locations. Now I've extracted the relationship between the potential set up by a point charge and then the charge that sets up that potential in the distance right over here. So it's a ratio of the amount of charge to how far away you are. And so if we're saying then that this quantity over here is going to be the same for both scenarios, well, then when we divide Q divided by R, we better get the same number as we kind of swap back and forth between our analysis in A and B. All right, well, if we look at that, we can notice that if we kind of like first look at this picture over here, well, we're a distance d away at this point. So if we then go to the next picture, right, by what factor have we changed the distance, r? Well, we've doubled it. So a times 2 in r. So it's effectively a 2r down here on the bottom, or a 2, I should say. Let's undo this. Okay. So r is going to 2r. I'll write it over here like this. R is going to 2r. All right, cool. And we want to keep the potential the same. So what do we have to do to Q? Well, you can see that in order to do that, we'd have to also have double the amount of charge. So the factor analysis here, these twos would cancel out, and we'd end up with the same. So we'd have to also have a doubling in our charge as we go from the picture on the left to the picture on the right. All right, so we've deduced now from just the potential map and then the distances reported that we have negative charges in both pictures, and there's actually twice as much charge over here on the right-hand side, which is pretty cool. All right, we'll do one more little question. All right, this question is really good. And let's think about the electric field at each location and where it's the strongest. Right? So take a look, and there's multiple ways to kind of think about this, but just think as simply as you can. Which location, and I'll give you 2 points here. We'll do, put this in red, this point here, or this point here. So back on that 90 volt, back on that negative 90 volt line, compare the electric fields between the two. Do we have a larger field by A at that location? Do we have a larger field over B, also on that negative 90 volt line? Or is it the same amount of electric field? And to really get it right, see if you can compare, the factors. So why don't we write out over here, let's do EA, the magnitude of the field at A is what factor different than at B? So what is that number right there? If you think it's the same, it would be 1. If you think the field at A is twice as large, you'd put a 2. If you think the field at A is half as large, you'd put 1/2. So work it out. You should have enough information to figure this out. And then you get a good test of understanding. So pause the video and try it. All right, let's take a look. And you got to be a little careful with this one. You want to really let the relationships guide your thinking here, because it's easy to confuse yourself in a problem like this, especially because you look at this charge QB over here, and we realize that there's twice as much charge over here than there is over here. So there's this tendency for people to want to think that there's a larger electric field kind of over here, but it's actually not a larger electric field here. It's actually a smaller electric field at this point away from charge B as it is at this point away from charge Q along that, or at the location of negative 90 volts for both of them. Okay, so let's see why. So over here for the calculation of the electric field set up by a point charge is QK over R squared, so it's the inverse square relationship as opposed to just the inverse relationship with potential, and then a direct proportion with the charge Q. So if we kind of look at our factor analysis as we've gone from one to the other, and we just use those parameters again, and we notice what's happening here, we can see that in our proportional reasoning we have a doubling in Q, so we get a factor of 2 on top. And then we have a doubling in distance, but because we have the inverse square, we have to obviously square that factor change, so we have 2 squared, and that's going to be 2 divided by 4, which would be 1/2. All right, so as we go from here to here, we see the electric field goes from E to 1/2 of whatever it was over on the left at A. So the electric field at A, to finish our result over here, the electric field at A, how would that be related to the electric field at B? Well, it would be twice as strong. So 2 times as much, since if we go from A to B over here, we're cutting it in half, while going back in the reverse would be a doubling, which is, I guess, how I wrote it over here. You could also write it like the electric field at B would be 1/2 of the electric field at A, also equivalent. All right, interesting. Now, pause the video and see if you can also think of it in a different way, conceptually. You might have almost seen it instantly that the field was going to be stronger. Oops, over here. Okay, the field is going to be much stronger at this point, around that point, than it would be over here, conceptually, from the idea of how electric field and potential are related mathematically, just in general. Okay, so pause the video and see if you can apply a concept we've learned for that. All right, so the real deep conceptual way to see this is to remember that the electric field value at a particular point is giving us information about how quickly the electric potential is changing at that location. And you can get a sense of that by just wiggling X a little bit, as I like to say. So for example, if you just make X change a little bit, like over here. It doesn't have to be x like horizontally. We're in one dimension here, so it could be anything in the radial direction perpendicularly to these isolines like this. But if you change that distance a little bit, kind of maybe like a little wiggle like this, I'll just, let's see, it doesn't matter what we draw it. I'll draw it right here. Okay. You can see that if we wiggle x around a little bit like that, we might ask the question, well, how much does the potential change by? Well, about by 10, right? 90 to 80 is about 10. Technically, we would be calculating the average electric field in this around this region of space there. And then we could do the same little wiggle over here. You got to keep the wiggle size, it's funny to say, about the same. Okay. And you do that here, and you can see, well, we're not changing by 10 volts now. It's going to be less than 10 volts. And so because of that, the average electric field around this area of space would be less because we're not changing the numerator here by as much as we did over here for the same change in the denominator. All right, so a real quick and easy way to kind of conceptually see that the electric field actually is going to be a little stronger over here. And that might be surprising because, there's smaller charge over here. There's not as much charge. There's half as much charge. But keep in mind, we're a lot closer to that charge to be on this negative 90 volt isoline. So therefore, when we work everything out, we get a field strength that's actually larger around this area. Now, going back over to charge B over here, it is important to note that if we were at this distance away from charge B, which is approximately the same as this distance as we are away from A over here, would there be a stronger field here? Well, yeah, definitely. Now we would be keeping the distance the same down here, so the same value here, which we could effectively ignore because it's the same between both. And then we're doubling the charge, so we'd have twice as much electric field at this point than we would at this point here. But notice, if we were to come in here at this point now, we'd be on a totally different isoline, which would have a much larger magnitude of voltage value compared to this one over here. So my question was really kind of comparing being on the same isoline of negative 90 volts respectively as we hop back and forth between charges A and B. That's what my original question was based off of. But now if we allow ourselves to change the distance, well, we would get different values. Okay, so the way you can think about that now is, here, if we were to do these little wiggles back and forth, we are changing our potential a lot more around this point. A lot quicker the potential is changing than it would be changing over here. So we'd have to bunch these little isolines all right up on top of each other, and they would be changing by 10 volts each one according to this pattern here that we've drawn. One way to kind of visualize that is, if you've ever seen like a picture of like a black hole or something like that, you might see something kind of like, like this, where it kind of like goes in like this, funnels down, kind of like that. And you can think of these concentric circles as like those isolines, and then where the field is really strong, the electric field is really strong, is where it's a lot of curvature, or it's real steep, I should say, compared to, a place where it's shallowed out here, where for the same little wiggle as you're seeing, it's just not as steep out there. All right, so that's kind of one cool way to think about these ideas. So then to back out, kind of like out here at this location, where the potential is the same value, we're seeing a weaker electric field, 1/2 as strong. So we would imagine we'd be at a shallower kind of steepness out here than over here, where it would be much steeper because that field is a lot stronger, which is cool. And then finally, one last question is, which direction would the electric field be? So draw two electric field vectors correctly. Let me just erase this one over here. So let's draw EA and EB. So draw the electric field vector here at point A. Which way would it point? And the electric field vector here at B. Which way would it point? And also get the relative sizing correct based on what we said before. And then we'll finish with an idea about the direction of the electric field and what information is related to the electric potential there. So go ahead and try that. All right, well, the magnitude of the electric field for B at this point over here on the negative 90 volt ISO line is going to be half as much as A, so we better get that right. My picture's kind of getting a little messy here. Probably maybe even a little bit more than that to get double. Something kind of like that. And the field always points into negative charges. So we'd have electric field vectors going into negative charges. Now, you can see how, based on just my choice of how long I drew this arrow over here, you can see how the field vector is like going past the charge. So when working with these problems, a lot of times you just don't end up drawing the electric field vectors close to the charge because it just clutters it up, right, as these vectors get larger and larger and larger. But I've done that here for some reason, so just watch out for that. But anyways, what's really cool is that the direction of this electric field vector, we could keep drawing it over here on this picture, probably it's a little bit easier to do, right? It's always perpendicular to these isolines. That's important to know. And to kind of connect that with the math down here, what it's saying is that if you want to walk in the direction in which you'll change your potential the quickest, which way should I walk so my potential changes in the quickest manner? Well, you wouldn't walk this way, right? You wouldn't walk parallel, because if you walked parallel to an isoline, you're never changing your potential. It's always just negative 90 volts, negative 90 volts, negative 90 volts, right? So these electric field vectors are pointing in the way that you want to move, so you change the potential by the largest amount. And that's perpendicularly always to these isolines, as you can see here. It's kind of like if you were, if this was like a real physical thing, this is like a black hole or something. It's like which way would you walk so that there's the steepest change on you, right? Well, you wouldn't walk around one of these lines. That wouldn't change your elevation, I guess, if you will. Or if this was like a giant canyon or something, right? You wouldn't walk parallel to one of these lines. You wouldn't change your elevation at all. You would walk perpendicularly, and then you would dramatically fall down. It's also analogous with like a mountain top or something like that, you know, like Everest or something. I don't know, whatever. You got these lines like this, right? If you've ever been on a really steep mountain, you can actually walk along the steepness if you walk parallel to where the elevation isn't changing. But the moment you faced straight down the mountain, then one little step and you are going to massively change your elevation quickly. Cool. So some nice analogies to kind of hopefully connect all of this stuff together. All right, so we'll end the video there. Hopefully you got something out of this on how electric field, electric potential, how these things relate together, and how we can use our abstract reasoning skills of proportional reasoning and these relationships that the electric field and potential depend upon for point charges to really kind of work through everything. Okay, so this is a good challenge for now, but hopefully you're seeing these things. All right, see you in the next video.